Welcome to the new unit, discrete probability. We'll talk about what discrete means a little bit later on, but the first part of this topic will be to just dust off the cobwebs a bit and do some sort of year 9, year 10, year 11 probability. So this is question 15 off a VCAR exam a few years ago. Here it goes. A box contains 6 red marbles, 4 blues. 2 marbles are drawn from the box without replacement, the probability that they're the same colour. So we're looking for red, red or blue, blue. Now red, red, the chance of getting a red first up is 6 in 10, followed by another red after that, which is 5 in 9. The chance of getting a blue first up is 4 in 10, followed by 3 in 9. So a blue followed by a blue. Now you can get that via a tree diagram, or you can knock this over pretty quickly by looking at the outcomes that you're really after. This is 6 in 10 times 5 in 9. This is going to be 4 in 10 times 3 in 9. And what we'll do is we'll stick those probabilities together, and we get the probability that they're the same colour is 7 in 15. All right, so you've got a minute and a half. I think it is on every multiple choice problem, but the faster you can do these ones here, this year 9 style probability problem, the better. All right, so the topic moves pretty quickly from revision of some old material to some brand new and exciting concepts. And it does, in 12 methods, take some interesting twists and turns. All right, so when we assume that the possible outcomes of an event are equally likely, then the probability of something happening is the number of favourable outcomes over the total number of possible outcomes, okay? Where A is the number of elements in the sample space, and this letter here, I think it's epsilon, is all possible outcomes. All right, so remember some basic prob notation. This thing here means union B. A union B is in A or B. This is A intersect B. Okay, so it's got to be in both sets. Probability of A is equal to 0. That's what we call something that's impossible. Probability of A equals 1 is an absolute certainty. Now, what we do is when we add together all our probabilities, the sum of all probabilities need to add to 1. Now this again goes through a couple of little bits and pieces. The probability of A greater than or equal to 0 for all events where A is a subset of the sample space. What that basically is saying is the probability of things that we're looking at will be greater than or equal to 0 when it's a subset of all of the sample space. Okay, so basically you can't get a neg prob. I say that every year at the examiner's reviews, that students will write down probabilities that are negative. Okay, the probability of the sample space is equal to 1. Sum of all probabilities of all outcomes is 1. Probability of the empty set, so this is called the null set, is equal to 0. Probability of getting not A is 1, take away the probability of A or A complement. And via the addition rule, the probability of A union B is the probability of A plus the probability of B, take away the intersection, okay? Otherwise you double count that intersection if you remember from last year. All right, when two events A and B have no outcomes in common, i.e. they cannot occur together, they are called mutually exclusive, okay? And I always use the example of if we look at the Venn diagram here, and in set A are the types of music that I listen to, set B are the types of music that you listen to. The probability of A intersect B, that is, if we had to pick a song that we probably liked, I'm going to dare say that that would be the empty set, that what you would choose and what I would choose would be, we just wouldn't find any agreement. So in this case, we say that the addition rule looks as follows. Okay, so the probability of A union B is actually the probability of A plus the probability of B. Okay, now again, I want to make sure that you're not confusing the terms independent and mutually exclusive. Okay, so these terms here, mean completely different things. Okay, so independence and mutually exclusive, don't use them in the same sentence. Well, use them in the same sentence if it's appropriate, but you can't say independent slash mutually exclusive. Same thing. It's not. Let's have a look at Venn diagrams and look at how they might be used to answer a question. So I've got event A is an even number when a six-sided dice is rolled. So let's go with A is an even number when a six-sided dice is rolled. So 2, 4, 6. Event B is a number greater than 2 when a six-sided die is rolled. So event B is going to be a number greater than 2, so 3, 4, 5, and 6. Draw the Venn diagram. All right, so here's A, here's B, and what we're looking for is, first of all, any intersection. Okay, so what do they have in common? 4 and 4, 6 and 6. We've got 4 and 6. We've got 2 in A only. We've got 3 and 5 in B only, and we've got 1 in neither A nor B. Okay, so this one here is the number of elements in A and B. That's how many elements are there in the intersection. The answer to that is 2. Notice it's not after the probability, it just says how many elements, N. All right, probability of A union B. Okay, so that's going to be there's 5 elements in the union, which is A only, intersection, and B only. So it's 5 in a possible 6 outcomes. All right, this is not A union, not B. Okay, now what does that one look like? So this one here, I'm just going to shade this. So first of all, I'm going to shade not A. This is A and this is B. So not A means B only and the outside. And B only, not B rather, means that and that. Okay, and what this basically is saying is, this is the same as saying probability of A intersect B not. All right, so that's looking for everything other than the intersection, which means we've got 1, 2, 3, 4. 4 out of 6 equals 2 out of 3. Now be careful with that one. A lot of students see that and think that that just means that it's just this one thing on, or it's the same thing as neither A nor B. So please note that probability of A intersect A, not A or not B, is not the same as the probability of A union B not. Okay, so it's not this. All right. So yeah, just watch out for that one. I have to do the Venn diagram still to this day for that particular style of problem. You might sort of go, yeah, I'm a person who only really does Venn diagrams. I don't use any other form. I like them so much that I refuse to acknowledge the existence of anything else. And that's to your detriment. So some questions really don't lend themselves to Venn diagrams. And so in 2018, this one appeared. It was Bo's Sheep and Goats. So Bo has a farm with 140 sheep and goats. Some of the sheep and goats have black skin and the rest have white skin. 42 goats on his farm, 8 sheep have black skin. And we found that, so the question was written as follows: draw a table or Venn diagram to represent this information. All right, so when students tried to do the Venn diagram for this one, what we overwhelmingly found on that particular exam is that students actually couldn't knock out the Venn diagram. They just couldn't get it working. For some reason, they couldn't work out. So this was like, what do we got? Sheep and goats. So if I go sheep and goats, that didn't quite work because how do you put black skin and white skin? Then they put sheep and black skin, which did actually work, but they got confused there. So this one here, draw it with a Venn diagram. What I'm going to do is not actually finish it off and say, is there a better way? So tree diagrams, fantastic way of answering questions with more than 2 events. Demelza is a badminton player. If she wins a game, the probability that she'll win the next game is 0.7. If If she loses a game, the probability that she will lose the next game is 0.6. She's just won a game. So we're starting here at winning a game. Okay, the probability that she'll win exactly one of her next two games is, so she's just won a game, she can win or lose. And from there, she can either win or lose. All right, so if she wins a game, the probability that she will win the next game is 0.7. So she's just won a game, so that's 0.7. If she loses a game, so that's going to be, so lose a game, so she's just won a game, so the chance that she wins the next game is 0.7. That means the chance that she loses is 0.3. Obviously, she's high on confidence after winning. Now, if she loses a game, the probability that she will lose the next game is 0.6. So lose means she lost a game. Chance that she loses is 0.6, 0.4. Obviously, you know, down on her confidence or whatever. So she's won, that's going to be 0.7, 0.3. Prob that she will win exactly one of her next games. So that can be win, loss, or loss, win. So win-loss is 0.7 times 0.3. Loss-win is 0.3 times 0.4. All right, that's going to be 0.21. That's going to be 0.12. 0.33 is going to be our answer there. So you notice that if you're comfortable with decimals there, it can speed things up. You just don't have to use the calculator to do it. Carnot maps or prob tables. Had a constant debate with Ms. Kerrigan, who was a huge fan of probability tables or Carnot maps, and I always used to sort of roll my eyes a bit at her use of them, but I have to agree or admit now, I won't probably say this to her, but I've come over to her way of thinking on it, and actually I've become a huge fan of the Carnot map or the probability table. Right, so notice that with a probability table, the events can only ever add to 1. So that's with a probability table. With a Carnot map, we do totals, or so that we can get a number other than 1 there. And I'll show you how that will work in this case. So this is the same question from before, but what we'll do is we'll approach it with a table and a probability table. So the question originally said draw a table or a Venn diagram to represent the information. Remember, we were struggling, or I personally was struggling with a Venn diagram. So let's try it with a table. So typically, you're going to sort of set up your template for tables. It's a 4x4, like so. Now, what have we got here? We've got Bo on a farm with 140 sheep or goats. The sheep and goats have black skin and white skin, so black or white. There's 140 in total. 42 goats on his farm. There are 42 goats, okay, so goats is 42. 8 sheep have black skin. Sheep and black is 8. The total number of white sheep and goats, so white sheep and goats is 120. All right, so let's knock out the rest of the details. So that means that has to be 20, that's 12, that's 30, that is 90, and this is 98. All right, so if we were to draw it with a probability table, so noting that if this was the instruction to produce a probability table, then it's going to look very similar. Except this time, sheep, goats, black, white. What's going to happen is that number there needs to be 1, and this is going to be 8 out of 140. So all of them have to be probabilities. 12 out of 140, 20 out of 140, etc. Okay. Now note that very rarely in methods 3, 4, I find that they actually tell you to draw a diagram as part of the question. what they do is they write the question and you choose the method that you want to use. Okay, so very rarely, in fact, I can't remember really seeing it that they tell you to draw it. So you can choose to draw it as a table or a prob table, but I have seen it come up in stacks, but you're not going to do a prob stack this year, so it doesn't really matter. All right, a group was surveyed about their drinking of tea and coffee. From the results, it was established that the probability that a person drinks tea is 0.35, drinks coffee is 0.6, and drinks neither tea nor coffee is 0.1. Poor people. Okay, so find the probability that a person from this survey drinks tea but not coffee, drinks both tea and coffee. So notice that there's no instructions on which way to go. What I'm going to do is draw up a table. So we've got tea or not tea, coffee, or not coffee, and 1 is our total here. So from the results, it was established that the probability a person drinks tea is 0.35, drinks coffee is 0.6, and drinks neither tea nor coffee, that's neither tea nor coffee, 0.1. All right, so this is going to be 0.4. This one here is going to be 0.3. This is going to be 0.05. This is going to be 0.65. And this is going to be 0.55. Okay, drinks tea but not coffee. So that's tea and not coffee. So that's 0.3. Both tea and coffee. Tea and coffee 0.05, which seems rather low. Seems to be a popular thing. Tea in the evening, coffee in the morning, but who am I to judge this? All right, lattice diagrams can be used for 2 independent events. Great way of determining sample space and at best used if all outcomes are equally likely. So we've got a 2 dice roll, and what we can do is then visualize the sample space. So this would be, say, roll, which one is this? This is going to be roll 2, that's going to be roll 1. So we've got roll 1 as a 1, roll 1 as a 2, followed by roll 1 is a 1, roll 2 is also a 1. Okay. All right, so find the probability that they are both the same number. So that is these ones here. All right, so we've got probability same is equal to 6 out of a possible 36, or there's a 1 in 6 chance of getting a double. Probability at least one number is a 4. Okay, so what we're looking for is one number is a 4, the other number doesn't matter. So we've got the 4s coming up here. So that's at least one number is a 4. And we've got the 4s coming up here. Now that's 6 and 6. So we've got a possible 12, okay, but this event would be double counted. So we're going to say that that's actually 11 out of 36 and remove the double count of the 4, 4, okay? So that will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Again, it becomes quite easy to visualize it if you've got that diagram drawn. All right, so get started on 13A, dust off the cobwebs, girls, and do those problems.